Hello, I am Philip Turner, and I am giving a presentation on nanomechanical computing. This is a presentation, it's sponsored by Virginia Tech, Department of Electrical and Computer Engineering, on an official undergraduate research course titled Nanomechanical Computer Subsystem, lasting for 1 semester. How did I get into this topic? It was in my freshman year of college. I was fascinated by the idea of making really, really small computers. Like, what is the smallest computer that could possibly exist? Would it be possible to make one that fits within a 999 nanometer sphere? That means that every single spatial dimension, every single part is separated by something measured in nanometers. I looked through a whole bunch of computing subspace, a whole bunch of options, trying to find really the highest packing density for memory and logic. One example was looking at magnetic memories, which are again, a new thing that's being developed, but there's one form that would work if it was separated by 100 nanometers, so each bit was separated by 100 nanometers from the next bit in a dense array. That was not enough for the device specifications. But if you try to compact them to 10 nanometers, each one separated by 10 nanometers, they would lose your data after a few seconds. Even if the device itself is small on the atomic scale, what matters is the separation between nearby devices in a dense three-dimensional array. One motivation for making a really small computer is an autonomous nanobot. To make that thing possible, you need to compact a lot of functionality inside a really, really small volume, like the size of a virus. And with existing technology, the most viable thing that I thought of was a protein transistor, which would be possible to self-assemble or use ribosomes or DNA origami to sort of make a complex heterostructure with protein transistors and some kind of memory storage. But it didn't seem like that was really viable in the volume of a nanobot. So instead, I was thinking about a microbot. So this would be like a shape-shifting bot that was several cubic microns, and it would travel through the capillaries, and it would be just small enough to be able to fit through the capillaries, and then it docks at a location, and it expands into a ring that's around 6 or 7 microns on the inside, where red blood cells can pass through without being obstructed. So technically you can fit the volume, the bulk of an electronic computer within the capillary, and then that big bot would deploy a smaller nanobot, which it remote controls with infrared light. And it would be able to control that nanobot for a few tens of microns, which is enough to service any cell within the vicinity of the capillary. That microbot would be covered in carbon nanotube antennas, pointing in every possible direction. Then I found this interesting article online. I was looking through stuff related to what I was researching, and someone did a very thorough characterization of the blood vessels in the human body. Mapped out these hierarchies of there's these arteries and these smaller things and these capillaries, and they have some number, and you can sort of address them in index and stuff. And one page talks about the viable size for a nanobot. So capillaries have a varying width. Some can be as large as 10 microns wide. Some can be 5 or 6. And the smallest one that on the tail end of the distribution would be around maybe 4 microns. And that means that any nanobot needs to be smaller than the smallest capillary that could possibly exist, because you don't want them clogging anything. The size that was proposed in a nanomedicine was around 1 micron in every spatial dimension, or smaller. And the power budget was 10 trillionths of a watt. Yeah, my device would not do it. The cost to make a photon was around a few zettajoules or maybe a few electron volts to make a 1 eV photon that would be the right infrared wavelength. And we'd be sending millions or thousands or millions of these in every random direction so that one of them would hit the nanobot. And then it would get a signal, and then the nanobot would, I don't even know how it would try to send stuff back. But I was just trying to think of what is the way you can actually make nanobots possible with existing technology. It doesn't seem like you can. So I read this book from start to end. The first chapter was like so fascinating. It went into like a whole bunch of technical depth, reviewing like the very beginning of medicine and what like it meant to be a doctor back thousands of years ago. And he characterized this so thoroughly that it was like, this has to be something worth, like something with a lot of technical depth. And then he got to material properties of things that would be suitable for nanobots. Now, diamond has some really special material properties. It's really stiff, and it is really chemically inert. Also, it's a very high atom density. Like the number of atoms per cubic nanometer is really high, and if you could form these atomic scale surfaces with atomic precision out of diamond, you could make enzymes or binding sites that match the shape of a protein with extremely exquisite accuracy. Also, diamond can make really, really small mechanical devices if it is atomically precise. The stiffness of the material is really critical to making these mechanical devices small, because thermal oscillations at the nanoscale, thermal oscillations dominate a lot of behaviors. And the stiffer the material is, the smaller the oscillation will be. Another thing, the bandwidth of getting data in and out of the human body. I've read a few papers about people using nanobots today, or like bacteria that are controlled from an external magnetic field. The issue is that magnetic field is sending around 1 bit per second, and it's sending to every single nanobot simultaneously. So if you want to send some nanobots to the brain, you have to have this magnetic field, and all of them will start like going in the direction of the field. They might like twist a little bit, do some kind of mechanics in the bot, but sort of like to get through the cells. But all of them are basically doing the same operation. And if you want to do like a surgery on like a whole bunch of different cells that all have like maybe a bunch of different conditions or different types, each nanobot would have to have a different input and different output, a different set of actions. They would really have to have their own computer on board that can, get data, compute, and do something with really low latency. The device specifications for one of the nanobots that Robert Feitis designed was it was a respirocyte, which is around 500 nanometers in 500 nanometer sphere, and most of the volume is either a compartment for oxygen or carbon dioxide. And on the inside is a small analog or very small computer that's controlling the gate to open and close where the carbon dioxide or oxygen molecules would come in and out. And the device specifications is a 60 nanometer sphere for the entire computer. That's like several orders of magnitude smaller than what could be barely done with existing technology. So it seems that if you want to make autonomous medical nanobots, or the kind of things that we're talking about in nanomedicine, you need to have atomically precise manufacturing. So at that point, I was skeptical of the idea of atomically precise manufacturing. The general view in the scientific community was not favorable, and I was no exception. I was like really strong. Like I'm going to dismiss any idea of atomically precise manufacturing, and only stuff can be built today with protein transistors and ribosomes building stuff out of proteins. But if I wanted nanobots reality, I sort of have to loosen up that opinion. And I gave Very Correct a chance. I got Nanosystems, and the first page sounded really reasonable. Talk about conservative estimates, making very pessimistic estimates based only on the laws of physics that underestimates the performance you'll get, but is more reliable. The second chapter talked about scaling laws. So explain what scaling laws are. A certain object has a volume. It's calculated by the length of the object to the power of 3. So if I have, say, a 1 meter object, 1 meter to the power of 3 is a 1 cubic meter. That is the volume. the surface area is all the faces on that. So a cube, a meter cube, would have 6 faces, each is 1 square meter. As you get down to nanoscale, the ratio of the surface area to the volume increases and becomes really, really large. And that's one reason nanoparticles are really good for catalysts, because they have a lot of surface area for the amount of matter that they have. But in nanosystems, the scale laws we talked about were like which kind of technologies would even be feasible at this range, where you need to have devices that are in a dense array that are all packed with a really, really small separation from each other. Electromagnets, the size of 10 nanometers would not be viable. The magnetic field strength is so low, like 10 to the negative 8 Tesla. I don't know the exact number or quantity he was talking about, but it was so low that it just wouldn't work at all. DC current devices could work sort of around that range. In fact, that's what we have now. Sort of around 10 nanometers separated from each other in a dense array. NAND flash memory is around 14 nanometers with each device, and that's really as small as you can get, because any closer and we'll start leaking current. Nanosystems said something similar, around 10 nanometer range or so. The DC current is just, it's not viable. You need to use electrostatic forces. One example of this was a computer theorized by Ralph Merkle. They use helical electrical fields to move electrons. It's actually the device is it's sort of like a charged device, but it moves around in a circle, and the way it moves is that it can move this like band of electrons that are moving inside of sort of like a helix, and they can use kind of logic gates in the way they interact. And it's just able to be a lot smaller because using electrostatic forces instead of dynamic electrical current. But at the nanoscale, you don't have to use electrostatic forces. There's a whole bunch of forces that can be used. The van der Waals force is really, really powerful. It acts at around 2 or 3 nanometers distance, and it's like gravity. It can be used if you put something just like a large number of atoms next to it. It'll be attracted, and if you can you can control the shape of whatever is attracting it, you can control it with the force acts. Polypropulsion force is actually the reason why something feels hard. Like I try to put my finger in the table and it's not going through. That's because the polypropulsion force between electrons prevents them from going into the same quantum state. They repel each other, and you can use these to balance each other. So instead of electrostatic attraction and repulsion, you have van der Waals attraction and polypropulsion. If you can make atomically smooth surfaces, you can really control the shape of the potential energy curve created by these forces. You can make it so it's really, really smooth oscillations. And if you have a rotating bearing, when the object moves, the non-bonded forces between the atoms on the outer ring will oscillate very, very little, and that creates something called superlubricity, which means the friction is just really, really small. Now it requires a lot of superlubricity requires a lot of constraints to satisfy, that the load imbalance isn't too big, so potentially the surface keeps being smooth, but it shows that you can make things with a lot less friction than would be possible than macro scale, just because it's atomically precise and you really control what's at the surface. It also removes damage mechanisms because you don't have atoms that are slamming into each other and breaking off. I found Robert Freitas, the guy who wrote Nanomedicine. He was a member of Institute for Molecular Manufacturing, and there's a website, imm.org, where he and Ralph Merkle had been posting some stuff, and they invented molecular link logic, which, according to the recent paper, it is 1,000,000 times more efficient than the cutting-edge transistor. And it requires reversible computing because it's so efficient that the Landauer limit is a bottleneck. The way it works is you have these gates that are like these. You have these links that are separated by acetylene bonds, so they don't touch each other at all, and there is no friction. And when they move, it's just like a single bond, single bond, and that single bond, like you can move freely. And they have this system where this block can, that top part there can move to the right, and it'll move into one position, but the bottom part is now spatially constrained. It can't move. this is sort of like a way to store binary data. You have one side is either the bottom side is moved or the top side is moved, and which side moves determines which bit it is. Made a whole paper on this, and they had like logic, like sort of logic systems, like a friction gate, which is a reversible logic gate. They had a 4-bit shift register, some very basic replicatory adders, and I was like, maybe this could be a nanobot. And I was sort of calculating the number of the atom count. I downloaded the molecular model and counted the number of atoms. That thing is, I think, 120,000 atoms, and if you could divide the volume of 1 cubic micron by that, by the atom count, you could figure out how many gates could possibly exist inside that volume. And it might just barely be possible. Except, I was looking at some other stuff that Robert Freitas was doing. After he wrote Nanomedicine, he got very into diamond mechanosynthesis. And I made a GitHub repo about it titled Diamond Mechanosynthesis Literature Review. And I looked through all the papers, and I was really fascinated by the idea of building stuff atom by atom, and how you could simulate some of that stuff on a computer. And he posted a lot of papers, and he suddenly stopped posting them in 2012, which was a little bit weird, and it's like sudden. The year after that was a patent was filed called US 2013 0178626, atomically precise products and methods and systems for manufacturing the same. The first draft was filed in 2013 by Robert Freitas and Ralph Merkel. In 2017, it was assigned to an entity called Nanofactory Corporation. And then in 2007, it was reassigned to an entity called CBN Nanotechnologies. Molecular Link Logic, they had filed a patent on that before they published to IMM.org and archive.org. And they all actually have well over a dozen patents, and some of them have over 10 different people signing. I don't want to be involved with this private intellectual property and whatever is going on behind the scenes. I need a public and accessible alternative to MLL. And that is the original idea for nanomechanical computing, invented by Eric Drexler in 1988. He gave a talk about polyine rods, which are alternating strings of single and triple bonded carbons in like a chain, and it's one atom wide, and it could add some functional groups like some extra benzene molecules sticking out the side. You could sort of have knobs that can interact with other rods. In 1991, he made a more refined version of this that's thicker. It uses diamond. Around 4 atomic layers thick is enough that continuum mechanics will start dominating behavior, and it's easier to model and reason about. Also, diamond is a lot less reactive than polyine. It doesn't have pi electrons. It's all covered in inert carbon-hydrogen bonds. I think this is a more workable idea anyway. The way it works is a physical obstruction of a moving rod. So in this image, the gray atoms, it's sort of pixelated, but there's gray atoms that are carbon and white atoms are hydrogen. And this rod wants to move, but the other rods have the ability to block it. And depending on which ones block it, you can get the functionality of logic gate. So that's a NOR gate. And that was like a really rough draft, just like proof of concept. I had a really limited compiler at that time, and I was able to do hexagonal diamond, and that unlocked some geometries. And I could build this thing on a hexagonal diamond. It's not very efficient. It's a single-use gate. The output rod that leaves machine phase as it's used, but it's just like understanding how to make something that can employ this mechanism behind rod logic. See the atom count there? number of atoms per elementary piece of compute is orders of magnitude smaller than molecular logic. In fact, MLL is actually not that much better than a transistors in terms of size. But this can shrink the distance between devices from 10 nanometers to 2 nanometers. And if you divide 10 by 5, you get 2. 5 is not that much in the grand scheme of things, but this is volumetric packing. So you have 5 in one dimension, 5 smaller in another, and 5 in the third. 5 to the power of 3 is 125 times smaller compute. And it's also, our logic is really, really amenable to dense arrays. It can get very, very high fan in and fan out. In fact, a multiplexer is like the ideal device for rod logic. It's perfect utilization of three-dimensional space with no sparsity, and it was actually the easiest to design. It's just so direct. You have these one fleet of rods that just get clogged in parallel, and then another one comes to the side and the select bits, and another one is the output bits. This is like such an elegant way to pack dense compute. It supposedly is not as efficient as MLL, molecular logic, but it's still efficient enough to land everyone as a bottleneck. So here is a 2-bit parallel half adder, which means it's a half adder that gets duplicated 2 times, so it's 2 different half adders running in parallel, and they're both clocked at the same time. And I took this system and I divided it into its 4 parts. The first one is the rods. That is the overlaying basically which rod connects to the other rod. The input, there's some input rods and there's output rods and there's intermediate rods. Patterns are the knobs, like which knobs will touch each other. The housing is what keeps the rods in place. And the drive walls are a mechanism for actuating logic rods. It uses the van der Waals force to pull them in, and then on the other half of the clock cycle, it'll push them out with Pauli repulsion. This was a drawing that I made of a nanomechanical computer, just trying to understand what all the where all the data will be sent, and what direction it will be clocked in. Each of these red arrows is 2 clock phases, and the data or the clock phase clock signal will go from there down to there, and then along each arrow, and there will be 18 clock phases. You hit that, it would store the data, dissipate a Landauer limit of energy for each bit, then it would go back on a reverse clocking sequence. I call that the reverse clock cycle. So one critical element of that is carry look-head adder. This is a kind of adder that it reduces the latency for the bits to for the carry operation to happen. And it does that by making stuff happen more in parallel, which has more volume, but it has a smaller amount of clock phases. I tried drafting that in Minecraft, and it was a bit challenging. It kept coming upon conceptual difficulties. I just didn't understand what was going on. I tried to take the 2-dimensional drawing and sort of overlay into a 3-dimensional denser packing configuration. That was the first one, and I tried I realized you have to have data going between other rods in 3 dimensions. So I did that, and I was still not unwieldy. And then I just gave up on the whole carry look-head unit and just how do I even get the input and output rods to be actuated? And that's what this image is. That was sort of when I got the idea of a drive wall. It's like you have a room, and the inside the room is the volume called the logic, and each wall can be sort of like a clocking mechanism that pulls all the rods in one direction, or pulls a bunch of rods in another direction. And you can clock a whole lot of logic rods in parallel with one very simple and direct linear clocking motion. So I needed to sort of grasp this idea of the carry look-head adder. I had to start from the basics. What is rod logic? What is it really at the lowest level? There's 2 things. There's the switch, which is 2 rods interacting with each other, either blocking or not blocking. And then there's a pattern, which is the knobs and inversion of signals. I started with this very basic idea of just a 1-bit, 1-switch piece of compute. And there are 2 things you could have. buff gate and a not gate. Also, I need to shrink the design space so that there's a small enough number of options available that I can enumerate each one and choose one. I can understand where's somewhere to even start that would do it. I need to sort of narrow down my options. One rule is that the 0 is always blocked and 1 is mobile, meaning the rod is able to move when it is clocked. So here, if this rod is able to move, this clock will move it from left to right. Inputs can be inverted by changing where the knob is placed so that in one position it could block it or it could not block it, depending on where the knob is. The outputs cannot be inverted, but so this set of rules is like, it simplifies everything, and it allowed me to start going through the basic logic gates. There's really two that stand out within this set of rules: the AND gate and the NOR gate. So the AND gate, in the resting configuration, the output is blocked by both inputs, and the position of the knobs is such that when they're clocked, they will unblock the output rod. And if both of them are clocked, the output can move in response to the clock signal. The NOR gate is the other way around. In the resting configuration, they are both not in contact with that rod. So if either one moves, it blocks it. This was a full adder. It's that's 1 bit length, it's not 4 bits in parallel like I was working before, just a single bit. What is happening? You have the first half adder, which is an AND gate and a NOR gate. And they both go to another rod, which, based on the way that it is patterned, it collects these outputs and it becomes an XOR gate. The carry input is the next thing that is attached in the circuit. And it goes to another half adder, which goes to the out. I also colored all the wool in order of the clocking sequence. So the lightest wool is the first, then there's the second, then there's the third, the fourth, and then the fifth clock phase. And this coloring the wool colors makes it really easy to understand where the rod should be positioned in order to have an actual clocking mechanism. Here I made a multiplexer, and it's a bit unconventional, a 5-to-1 multiplexer. You don't see that often. You see 2-to-1, 4-to-1, 8-to-1, but I didn't want to have to place all the blocks in Minecraft for 8 bits. I still want to shrink it to 4 to 5, but I wanted to be as complex as an 8-bit one. And here I have 5 different inputs, and each of them can be actuated, but whether they actuate is actually determined by the select rod. So this black set of rods here is actually actuated before then, and if it is there, it's sort of going to block the inputs. And the output collects whatever the rods do, and that is a mechanism behind selecting a lot of input signals, and then it goes to the output. This is also really, really dense. Every single slot in the array is filled with a switch. There is 0 sparsity, and this is like really easy to design and scale. Logic units are also similar. It's sort of like a multiplexer, but each input in the multiplexer is a different binary logic operation. There's OR, AND, XOR, NOT, these kinds of basic 1-bit operations. And this is something that's used in computers is just a logic unit for basically do bitwise operations on the lanes. And you can clock multiple bits in parallel with the same operating select signal. And I annotated the inputs, where the inputs are, and then where the outputs are. Next is a 2-bit carry, ripple carry adder. So the inputs, each is a half adder, and the half adder gets clocked, and then it sends its data to the carry chain. And the carry chain, it computes something, and then it sends the data to the next layer. The way it does that is the rod has knobs not just on one side, but on both sides. So it can interact with other bits of logic on its own layer with the rod on the bottom, and then with the knob on the bottom, then the knob on the top can interface with the layer above. So that is a way that I can send data between layers and progressively chain up to an infinite number of bits. I also put this in a four-bit ripple carry adder. I wanted to see that, like, actually see this in action, see the rods moving and blocking each other. In Minecraft, there's something called slimestone, which is it's where you can make circuits out of slime blocks, which stick to everything that's attracted. They stick to everything, and they pull all the blocks that are attached to them. And I could make that be like a logic rod, where the blocks that are attached are knobs. These green and yellow kinds of slime blocks are incompatible, so they won't they won't interfere with each other. They're just like separate entities. And I can make alternating sets of green and yellow slime blocks that can act as different stages of logic. And then I can actuate these with pistons and with redstone dust. This is an output interface where each of these lamps was one of the intermediate signals. And the reason I created that is so I could debug every single little motion that happens in the computer to make sure it's going right, going in the order that I want it to go in. And then here I have the outputs. These are the sum bits. There's 4 sum bits, and then there's 5 carry bits. Carry in, carry 0 to 1, carry 1 to 2, carry 2 to 3, carry 3 to out. This was a really good debugging experience. I put a lot of time in. I think I created the entire thing in 2 hours, but a lot of that was just getting the user interface right. I wanted to make sure that when I was in that debugging feedback loop during that testing stage, that I would be able to just see what the outputs are. Like, it's not always obvious, but you need to make these computer devices amenable to looking at them and seeing what the input is and what the output is. This is the input interface, where each lever could activate one of the inputs, and then here, each one would manually activate one of the clock phases. So I would put this, and put like that was a 10-phase forward clock cycle. The reverse clock cycle, unflip that, unflip, 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 unflip. That is a retractile cascade in reversible computing, and that is a successful implementation of a forward and reverse clock cycle. Reversible 4-bit adder. One issue though is that it has a lot of clock phases, because the ripple carry, each part of that is 2 different clock phases. And if you chain this up, it's going to be a large number of clock phases, which makes the clocking circuitry a lot more complex or bulky. So now it's time to go to the carry lookup adder, which I was originally going for. It was still really hard to figure out what to do. I realized I need to have logic rods in all 3 spatial dimensions. This was one of the earlier prototypes. I needed to like organize all the generate and propagate signals. So a half adder, you can think of it as having a NOR gate and an AND gate that together are hooked up into an XOR. But another way to think about that is one is a propagate, and the other is a generate, and you can make these sets of logical statements based on propagate and generate in each of the half adders. You can predict what the carry bit is with a lot lower latency than a ripple carry adder. And the way to do that is I organize these propagate signals into one unit and generate into another, and then there were these logic rods in the back that would collect up all of the knobs on the applicable generate propagate, and they would do that logic statement, that big, massive AND statement. It took about 6 to 9 iterations in Minecraft. I got to this, where the generating and propagate units are perpendicular to each other, and that makes it be a lot more compact. The fan outs, or the length of the logic rod gets much shorter, and it's much more viable to clock. Now I'm starting to think about what is the order I'm going to do things in. If I have a clock signal, I want to simplify the mechanism of clocking as much as possible, and one assumption is that it has to be done by a piston that moves forward in the forward clock phase, and then when it moves back, that's the reverse clock phase. So here we have the inputs. That is the start of the computation and also the start of the clock cycle. The drive walls are sort of depicted by these different colors of wool on the top, like yellow and green and orange, and they it sort of collect up all the things that need to be actuated into like one single signal that will ultimately originate from the piston. And they all have to actuate in the same order in space and time. I went through another design iteration, and this was a lot more clear. It's just like, it's not a lot neater. I can really see where the clocking is. There's a red thing that is, it actuates two arrays of rods. These are actually four bits happening in parallel, but the orthographic view sort of hides that there's multiple rods. And this thing's gonna move up in this direction in response to the clocking. And here it's actually gonna, two things are happening. This whole set of glass blocks is gonna move this way, and then the drive ball is gonna move that way, and the source of that motion will be that very, very compact piece of clocking circuitry. The other side was also able to sort of compact that into its own localized unit of hardware that can have a lot less spatial overhead. These ones sort of clock a little bit after those, sort of in sync, and I could make the whole track that some of these move be a lot smaller. So these are going to go 1, 2, 3, 4, 5, 6, 7, 8. Yeah, the number of clock phases went down from 10 to 8, which is it's good, and that's sort of what the whole purpose of a carry locate adder is. 4 more design iterations, this time in atomic detail. These are all rods of diamond, specifically hexagonal diamond, 4 or 5 atomic layers in one dimension, 4 in another, and they are laid out so that there's enough housing in between them to separate them and make sure that they are positionally constrained despite thermal motion. A lot of design iterations were just trying to get the layout right to get enough space between them. This was particularly tricky. Right here, these are actually some of the rods that send the propagate signal between parallel bit layers. The first time I tried compiling it, I got these rods and I sort of made these holes in the housing where the rods would go, and I got these floating blocks of atoms. That is not good. It's an artifact of compilation, and I need to revise the design so those blocks of atoms don't happen. And this is a very refined result of a lot of trying things, writing code for it, and starting over from scratch with a better idea for what to do in the next design iteration. One thing I learned is a lot of the time spent designing this is not spent on simulations. It's spent on compiler engineering. Just getting atoms in the right place is a non-trivial task. Around only 1% of the time is spent doing molecular dynamic simulations, which is a lot lower than I had expected. The reason for this is going to go on an aside. The format that the data is stored in with this kind of nanomechanical hardware, it's not very amenable to representation as a triangular mesh. It's very different from typical mechanical engineering in that the regular point-and-click CAD and finite element methods are not really well mapped to this idea of atoms and bonds connecting atoms. Atomically precise systems are pieces of software. Every atom's location must be known exactly and stored exactly to set up a simulation or to generate a build sequence. Matter becomes information, and it must be treated like information. Here I have some code for the housing structure. It takes all the rods and it creates a conservative extended volume from the rods as a whole where the rods will move in. And it takes like a very large block of diamond with some manually coded chunks cut out to minimize atom count, and then it puts all these holes in the lattice. And the way it does that is deterministic. If I don't change the code at all, that set of atom generated is going to be the same. I can create a hash out of these atoms in this lattice. There's a function that takes the atom types and atom positions, and it creates a unique 384-bit hash value. And then I can energy minimize it, which takes around 17 seconds of latency, and I store the minimized structure on disk. And the next time that I start the compiler to retrieve that minimized structure, with negligible latency. This time before I started this project, I came across a paper titled "Why Mechanical Design Cannot Be Like VLSI Design." It talked about the history of electronic circuits and electronic design, and sort of the golden era around 1980s, 1990s, where it wasn't really dominated by the material science and reaching laws of physics. It was just like you're scaling at Moore's law rate, and you just pump out the next processing node every next few years. Throughout this process, people just made these high-level abstractions, and they were able to scale these basic logic units to billions of transistors. And this hasn't really happened with mechanical devices. The largest ones to date are around a few thousand components. The reason for that is that these mechanical devices, they're all tightly coupled with each other. The performance of one depends on the performance of the other, and you really want to optimize performance for these mechanical machines. Subsystems are not separated. And I was worried that that would happen with nanomechanical devices, but it's also mechanical. But Rod Logic breaks this rule, because I use VLSI principles to simplify the design. I separated it into 5 different functional blocks: the input unit, the generate unit, the propagate unit, the carry unit, and the output unit. And on the previous slide, these are actually different data structures in the code, and each input is labeled with a comment that describes what it does, what its purpose is, sometimes even which other rod it connects to. And I can separate these different functional blocks and debug each one in isolation. It's sort of what happens with VLSI. One reason why this is possible is because Rod Logic has a much higher panout than MLL. It's very obvious how you can make something connect to another unit without really having its behavior defined by the other unit. You can have one subsystem that connects to multiple other subsystems in a controlled and separable way, especially if the housing is stiff. The reason why I separate these things by such large volumes here, like this is more than twice the width of a logic rod here. It's because I want to make them isolated so that I can make these higher level abstractions without worrying about them getting coupled and messing with the approximation. So earlier I talked about how one solution to getting data between different layers was having vertical logic rods. This wasn't really obvious in nanosystems, and that's why I had to come up with the idea on my own. But one issue is that with the hexagonal diamond, one of the ways you can cut it is you can sort of cut knobs out of these 4 atomic layer rods, and when you sort of cut this pattern out of it, the smallest one is 3 atomic layers, which is also good enough to have a continuum mechanics apply and to be stiff enough for its use case. But when you put the knobs in one dimension, it's really simple. They form 6-membered rings and all the conflicts. When you do it in the other direction, there's 5-membered rings. And to do vertical logic rods in the configuration of that unit, I had to have one rod which had knobs on 2 different perpendicular directions. So some of these knobs had 5-membered rings, which shrink the lattice constant, and they cause warping. In this image, this is without fixing it at all. This thing is going to warp, and that's problematic. I mean, when you put it in the housing is probably going to force it into a rectangular shape. But when you're trying to assemble it with a piece of robotic machinery, you want the robotic machinery to be as simple as possible, and if possible, don't have any rotation. These things would have to be rotated to go into the housing, or they would sort of bump in and maybe. I don't like the shape of that when thinking of how this will be assembled. Now solve that by placing silicon atoms at 5-membered ring sites. Silicon atoms are larger than carbon, and they expand the lattice constant. So there's 2 different things: a shrinking and expanding the lattice constant will cancel each other out. I call that counter strain. But now there's a third problem in that I fix warping along one direction, but now let's start warping along a different direction. And as I add more of these knobs to each other, the warping keeps adding up, and I have these rules where I sort of add more restrictions to what I can do to sort of counteract that. It becomes really unmanageable. Sometimes you want lattice warping to create strange shell structures that are stable kinetically. With linear sliding mechanisms, warping is not a good thing. Here I have 3 different rods that were taken out from one design iteration of the CLA. And they have all gone through the energy minimizer, and the warping is very hard to notice. There is a little bit. If you can sort of imagine there, it's like maybe 1 or 2 degrees on that bottom rod. But it's almost no warping. And also, there's 4 to 6 phosphorus atoms there, compared to what was previously 2 silicon atoms. What is going on, and how did this fix the warping problem? Phosphorus is one of the few non-carbon elements that is easy to simulate accurately. The pure number of parameters in MF4 was a lot smaller for phosphorus and sulfur than for these other elements, so I ended up just not doing these elements. But for 2 ones, silicon, phosphorus, and sulfur were really good to say, like, I have parameters, and I'm pretty confident that these match what's actually going to be an experiment. And I would rather choose elements that I can have the simulation be a better approximation of reality. So within that context, phosphorus is better than silicon. The phosphorus atoms are placed on the surface, and in order to maintain the same extent volume, I have to either have silicon atoms on the interior or phosphorus atoms on the surface, and I can't do silicon atoms on the surface. So that means that silicon atoms, whenever they are possible to be used, are going to be on the interior, in a place that has 4 different covalent bonds. That imposes some kind of geometric constraints that make the lattice warp in a much more severe way. With phosphorus on the surface, there's 3 covalent bonds, and it can sort of move out of the way. The warping can sort of relax in a localized manner. The surface is less stiff than the bulk, and it can absorb these deformations, and it can the effects of this warping is less long range. So these knobs they're no longer interacting with each other. Remember that with the VLSI, the decoupling subsystems is the key to scaling. You can imagine this as a system. Each dopant is a subsystem of the knob, which is a subsystem of the pattern. And these subsystems must be isolated to create higher level abstractions that are workable to design. Energy efficiency. You can make something as small as you could possibly want to make it, but if it consumes a lot of power, then it's not going to be really viable for personal computers. What you really want to do is make a computer that's really, really efficient, and if possible, also really, really small. Before getting into this semester, I had done some work on reverse engineering the Apple GPU architecture and comparing it to other GPU architectures like NVIDIA and AMD, and just comparing like the number of watts per elementary number of floating point operations. And Apple was the most efficient by like a factor of 2 compared to every other vendor. The reason they do this is a clever use of low clock speeds and small caches, and always being on the smallest semiconductor node. Here is the GPU. It's actually around 25% die area. This is the chip that Apple says is like most GPU. Like it's almost entirely GPU, and the CPU is like just this top portion. But the actual the actual area consumed by GPU cores is only a quarter of the chip. So it really feels a bit strange, but it's just the way the geometry works out. It has to be that way. And then this is taken directly from Apple. I'm pretty sure that this is with all the ALUs being utilized, and the clock. The clock frequency is the only thing differentiating the low power from the high power. It's really hard to reproduce low power estimates. I'm not going to get into that, but I'm just going to use that, and I'm going to say that this estimate is pretty accurate. The energy per switching operation in Apple GPU, which is a really good representation of the latest semiconductor nodes, and it's really, really efficient version of a computer. As good as you can get is around 2,000 zeptajoules. That's 10 to the negative 121 joules. It's a unit that I use a lot at this scale, and 2,000 is a lot larger than the Landauer limit, and we're reaching almost at the limit of how small we can go. Decreasing the clock speed, Apple has used this. They go to the extremes for power efficiency. Like, you would not believe how ridiculously they do the hardware and software combined to minimize the number of watts in the processor. And going from 1 gigahertz to 300 megahertz, unless I am mistaken, it only decreases the energy by a factor of 1.3. And even if it's not true, just 2707 divided by 4 is still a lot larger than the Landauer limit. So I'm going to go by this estimate. I'm going to say that is pretty reasonable a way to describe electronic computers right now. How efficient can they get? I am assuming that if you drive it even lower, I think Apple's already driven it to like the extremes of how low and efficient you can get, and going lower is not really going to change the power efficiency much. Higher clock speeds, on the other hand, the power increases exponentially. That's why with these other GPU architectures, when you tune the clock speed to the extent that Apple would have done, you will get massive differences in energy consumption, because it's a very large polynomial of the clock speed. So I put greater than 10,000 gigahertz at 3,007 joules per switch operation. I didn't even consider these high clock speeds in any other comparisons. Still, at every single clock speed, it's still larger than the Landauer limit. I don't know if this is a limitation of electronics in general, or just the limitation of what you can build with lithography. For raw logic that's supposedly inefficient in comparison to molecular link logic, these numbers are orders of magnitude smaller than transistors. And you can exploit lower clock speeds really efficiently with raw logic. This was a design that was optimized for a really high clock speed. So the energy dissipation modes that are the lower orders of the polynomial are not really optimized. But you can imagine that if you redesign this so that the friction was larger relative to clock speed, but the other things were smaller, you could get the energy consumed per operation to be a lot smaller as you scale down to lower clock speeds. From some of my simulations, just general intuition with working with molecular dynamic simulations, these numbers do seem reasonable around 2 joules per rod. Actually, I found a typo in Nanosystems relating to this number where he put 0.013. It's actually 0.13. And with this correction, the estimates seem a lot more believable. I fixated over this number for a long time, and I didn't understand why it was 0.013, but if you change it up to factor 10, it makes sense. And actually, he did derive the second number after that from this, but it was just, for some reason, the 0 was added in the text. It doesn't really change the grand scope of things. It doesn't really change the qualitative capabilities at the systems level. It just changes one quantitative estimate that I fixated over for a long time. I'm going to say that this takes a lot of trial and error to make efficient systems. These numbers will be plausible after several rounds of optimization with working piece of logic. Also note that this number is derived by taking the number of taking the energy per rod and dividing it by 16, because Nanosystems has really dense logic arrays with very few inputs and a lot of switches. Imagine a 16 by 16 array of switches, where there's 16 inputs and 16 outputs, and each rod owns a very large number of switches. So you take the energy per rod and you divide by the number of switches. That is the energy per switching event. This is lower than the Landauer limit. With my 4-bit carry look-ahead adder, the number of switches per rod is around 4 to 8, which is not as great. So I can imagine that this thing would have to be corrected to something larger for that carry look-ahead adder. But that might not be the only way to design a computer. Multiplexers, as I said, are really elegant ways to scale really dense compute, and that might be able to get more switches per rod. So putting all this in context, according to the theoretical calculations, rod logic is 15,000 times more efficient than CMOS, which seems a little bit hard to believe. And I wanted to be able to test this in a molecular dynamics simulation. Obviously, the simulation is not a replacement for reality, but given that these are really, really hard to build, and it will take a lot more effort to be able to build and scale systems that can make these simulations as close as you can get. Looking at molecular link logic, I don't even have a quantitative estimate for that. They give one parameter for friction coefficient and then just assume that no other dissipation mechanism is going to dominate. Even if it is 1,000,000 times more efficient than CMOS compared to 50,000 times, the bottleneck is going to be the Landauer limit in the registers. Registers, when you do an operation, you have to store the data somewhere, and each register is going to dissipate ln2 kT of energy, or the Landauer limit, 2.8 joules. So I think both broad logic and molecular logic would be bottlenecked by the registers. So if you want to optimize your efficiency, you should put more focus on the registers and not really the switches themselves. So to wrap this up, two different clock speeds that are proposed. 1 megahertz, I think, is almost certain that it can be really, really efficient. 1 gigahertz was actually proposed in the United System, and it should also be more efficient, less than Landauer limit for switching operation. As long as it employs reversible computing, which I proved with that Minecraft demo that geometrically you can get a reversible computer with rod logic. Lucky loop logic is not the only way to get reversible computing. One question that I don't fully understand is how kinetic energy can be recovered. You can imagine a spring that has it has energy, and in the middle of the oscillation, it's all in kinetic energy. The mass is at the center. And then it goes to one apex, and it's all sort of potential. Then it goes back and goes to the other apex. And it can temporarily have large amounts of kinetic energy that allow it to move from one place to the next really fast within a short amount of latency. And at the end, it's going to be recovered in a spring. In the next cycle, it'll go back into energy and stored again. And that will be one easy way to recover energy. I don't really fully understand how this would work with the system of drive walls, clocking rods in a one-way cascade. I think I sort of intuitively understanding how it might be possible. If you move slow enough with forces work, it's really hard to explain my reasoning, but it might be possible to have kinetic energy recovered with the way I designed this. I'm not going to go into that in a lot more detail. I was hoping to be able to test this semester, and one way to test this is to make a system that obeys the second law of thermodynamics. So as an isolated system moves forward in time, the entropy must increase. And that entropy is really the source of the Landauer limit. As long as it's isolated, nothing else interacting with it, the entropy should increase and useful energy should be wasted into thermal energy. And to do that, you have to have the power source be part of the system itself. Rotational or angular kinetic energy is really, really dense for a mechanical computer. There's a paper that Robert Feitz did about energy sources or energy density, and there's a graph of mechanical energy sources, and there were a whole bunch of points, and it was like a gap, and then the very, very top part of the graph was rotational kinetic energy. It was like an outlier from the rest of the graph, and then it was so dense. That just proves it's really well suited for this. And that I went through one full design iteration of a flywheel system with the flywheel, connecting rod, piston, and housing, and it took a lot of time to compile to just get the geometry right, to fix the issues with the static structure. I put it through a simulator on an AMD GPU, and the first time was I was running at 10 gigahertz because there's some issues with the energy rising in energy generation simulation. Like the kinetic energy would keep rising because of numerical instabilities, and it failed completely. And that was expected because 10 gigahertz is above reasonable operation speeds. Then I went to 3.2 gigahertz, and I was planning to go successively smaller logarithmic jumps to smaller and smaller clock speeds until it became computationally intractable. And around 3.2 gigahertz, it became computationally intractable because in energy storing simulation, you're not allowed to mess with the system. It can either be isolated. You cannot create an NVT ensemble. It has to be NVE ensemble. And because of really large time steps, that energy is going to start not being conserved, and it started drifting. The temperature went from 300 Kelvin to 700 Kelvin. That's why I had to restart resimulation with lower time steps. I found that the compute cost with respect to time scales quadratically with time with a second order integrator. To simulate longer time spans, not only to simulate more time, you also have to simulate smaller time steps. So it became the point where it's just not workable. So I think if I want to go over this again, I have to figure out, make a better integrator that has a better order scaling with time. I don't really have a lot it's sort of out of scope of this one semester. I was going through a second design iteration that would at least fix the complete catastrophic failure mode that happened in the simulation at all clock speeds. And this second iteration would have a planetary year system. Unfortunately, I wasn't able to finish that in time, and I had a session with a flywheel, but since this presentation was getting really, really long, I decided to delete that section. This presentation is about linear sliding mechanisms anyway. No rotary links and joints, just linear motions that are simple and direct and simple to manufacture with like layer by layer manufacturing. So I'm going to end this presentation with an orthographic view of the entire 4-bit carry look-ahead adder system. The smallest 4-bit adder permitted by the laws of physics that I am aware of. It is smaller than a virus, 26 nanometers by 13 nanometers by 21 nanometers, without the derived walls and patterns, just the logic, like the layout of the rods all troubleshooted. So as a result of months of compiler engineering, a self-contained set of source files that can generate the static structure for a 4-bit adder. I've not tested whether this works correctly or efficiently, but I've reached a point where I can now enter an array of atoms in the simulator. Seems like something simple, but it requires all this work just to get an array of atoms in the data format that's required, and get data structures that can be used to make a workable scripting workflow to move these rods and everything. So now I have the means to start trial and error, fixing bugs, finding what doesn't work, and revising it to make it work correctly. And after all that, then optimizing energy consumption. This was the first time in 30 years that a major university has sponsored molecular nanotechnology. Last time was around 1991 with Eric Drexler and his thesis on molecular manufacturing. It was an honor to be able to work on this project. And that concludes this presentation.
Does anybody have any questions?
I do.
Yeah.
You don't really cover this in the talk, but I'm curious, you talked a little about flywheels at one point. I'm curious what you see as powering the motion of the rods.
I don't see flywheel in practice. The reason I choose the flywheel is because in simulation, it's the way that I had to set this second law of thermodynamics is, I think the mechanical energy sources, because they're part of molecular dynamics, it's just really the only way to get this kind of obey these kinds of constraints to make a more rigorous mathematical proof. I think nanosystems talked about using electrical signals to sort of get power. It's actually designed for a DC motor. Instead of an AC motor, you need a DC motor to scale the way that these certain kinds of ways of getting current scale. And you would use a DC motor with like a macro scale thing with like electrical current driving things at like these say micron distances or millimeter distances. And then at the one point they would have these you have a DC current device that would generate rotational motion. And there would actually be a flywheel as a method to buffer and sort of smooth out irregularities in power dissipation, but the principal mechanism for storing and storing energy would be electrical. And the compute itself would be mechanical, because the compute itself needs to be as dense as possible. The power can be much more bulky.
Yeah, that's what I was wondering about, is how big is this when you actually have the power systems and the communications to the outside world?
Actually, I had sketched the flywheel on my iPad. I was sketching it around, and the first time I went through it, it was around 6 million atoms, but I used the principle of same relative deflections across scales. So if you have a mechanical device, and if you apply scaling laws to it, at any scale, whether it works or fails basically has nothing to do with the scale it's at. It's just relative geometry, whether certain parts are stiff relative to each other. And I could use this principle multiple times to take what was very, very large compound structure and shrink it down by a factor of 1.5 in each spatial dimension. It doesn't sound like a lot, but 1.5 to the power of 3 is around 4. So we shrink the atom count from like 800,000 to 200,000. I did that with this, and I think it might be possible to get a gearbox that's sort of the size of this 4x4 array, and it would the gearbox would be able to take a larger source of axles taking power, and the gears would sort of transfer it into the outer ring in a more it would sort of have a lower clock speed, and it's just a way that's more efficient and has greater mechanical advantage. And at the very end of that, these planetary gears would sort of the planet ring around them would be a cam surface, and it would be able to power 2 different pistons that are all moving at the same time according to a reversible clock sequence, and they would be what I talked about earlier with here. It would on the outer sides of the planetary gear, the left would be a piston that is sort of connected, and it would be actuated by the cam surface going from here to here, and it would this would move from here to here, and that would move from there to there. I haven't to really figure out whether it's possible. I'd have to get it in more atomic detail, which requires a lot of different parts to be compiled and then set up in a simulation. But I think that within this general design space, it should be possible to make something that is workable.
Can you go back to your last slide? I have one other question. So like, what's the tolerance here between the rod and the channel itself? Do you worry about bonding because it's so close?
Actually, that's actually a really optimal distance. This is highly concentrated diamond, which is really inert. Imagine oil molecules that's slightly concentrated, it's so inert. And I made sure that I passivate all the surfaces with this. Like there was that thing with the phosphorus dopants here. That should be chemically stable. The lone pair should be chemically stable in that electronic configuration. And if it's not, you would have to go with a little bit lower performing rods, but I'm pretty sure that should be stable. And also that it would fit within the extended volume. Because these rods are connected to the housing with
it looks like you're very close, so you're gonna get interface effects that are non-trivial.
But
There's a class in here at 12:30.
Okay.
No, actually,
So
that's a
we are
good
going
point.
to need to.
Because this is
make
exactly
papers.
diamond.
Yeah.
And the housing is cubic diamond, which means that it's the way that it works actually has lower friction because they're not the same crystal phase, and that's the mechanism of superdiversity that's talked about with ferrites. And hopefully that will apply. I haven't actually measured it in much of the.
That's actually what I would like simulate. The simulation, like I would love to see for this. It's very simple. It's just like one of these rods sliding along a surface.
I actually did
of
do
similar
that.
material.
I did do that. I just didn't do it in a way that could have like clocking. I did that to make sure that the non-body interface would accept the rod and that it would be in a
That's something absolutely to show in this talk.
Yeah.
If you do the talk again, is that little check.
Yeah.
Thank you very much. Excellent talk.
This was incredible.
Yeah,
My mind just like I totally love.
Yeah.
Yeah.
And if you're curious about stuff like this, there's a nanoscience department. That's where I know Philip from.